Today's speaker is Richard Gibbens, and the nice bit about this talk is it's not another talk on stochastic block model estimation. We're going to challenge our inventiveness a little bit more and hear about capacity bounds and robustness in multipath networks. Thank you.
Okay, thank you very much, Sophie, for the introduction. And yes, I'll stretch our boundaries to some other topics. And the key sort of topic or background theme for this talk and some other work I'll be referring to, I think, is the idea of resource pooling or load balancing as a way of enhancing the robustness and resilience of networks. And you can see that in operation in road networks, for example, where vehicles will split across different routes between their given source destination. So, for example, when I cycled here from the computer laboratory, I cycled north of the Cavendish. I could just as easily have cycled south of the Cavendish. And there's a sort of a certain amount of load balancing that goes on between people taking the same essential travel between that source destination pair, but using different routes. And when things become congested, or one of those routes, for instance, is being closed for maintenance or something, then there's an ability to switch routes. So the presence of path diversity can be very helpful in networks. You see that in the road transport context where buses and car vehicles will spread themselves around congested hotspots to try to spread the load according to their perceived expected travel times. But what I'm going to talk about today is not so much driven by the data, say, we observe in road transport networks, but to look at some modelling studies of communication networks where heretofore the routing has typically been on a single path between a source and destination. And what would be the potential in a communication network if we allowed it to, as road users do, to spread themselves across multiple paths between the same source destination pair? Does that bring performance benefits? Does it bring robustness and resilience benefits? And we'll see how we can deal with that in the talk. Specifically, what I'll be doing is dealing with a protocol motivated by packet networks, internet packet networks. And there's recently been a lot of work on the idea of what's called a multipath version of TCP, which allows us to do exactly this, to have multiple subflows between a given source destination pair. And my co-authors, I should mention, for this piece of work are Bejan, who was a postdoc working with me on this project, now works for Smith Industries, which is a very fine consulting unit for industrial maths area. And two other colleagues, Robert Hancock from Rope Manor Research in the UK, and Don Towsley from the University of Massachusetts, Amherst. And together we were working on a project investigating this multipath robustness. So just to bring some of those ideas together, the ideas of resource pooling with multipath. So the idea is that the traffic for a connection, so a connection is a file download or some transfer of information between a source and a destination. That traffic is split across a number of subflows. And I'll give that number the name little n, because that will be a useful parameter we'll talk about a lot in the talk. So how many subflows would be appropriate would be a sort of question we're trying to answer. And what we're striving to do by using resource pooling across a number of subpaths that may exist in your internet network is to gain greater utilization of the resources, but also to allow the ability under varying conditions in the network, say failure conditions or traffic overload conditions, for the pattern of traffic to adapt to the available resources, which might be themselves be time dependent and somewhat unpredictable. And we discuss how to achieve these goals, and in particular illustrate a model corresponding to the subject, the number of subflows n. As we increase n, we expect to have more robustness, but does it saturate, for example? And how big does n have to be? Because if n is very large, then there's a greater and greater sort of coordination problem for the protocols themselves.
There's a famous paradox whose name I forgot, that when you increase n, sometimes the equilibrium is worse than before. Do you know that?
Yes, but maybe you're referring to Bray's paradox?
Right.
Yes, so certainly that can occur in communication networks, and in particular Braze was a road transport engineer, so he described that. So that would be an example where if you allow completely decentralized actions on the part of the road users and you installed more capacity, then everyone could, under some circumstances, be worse off in terms of their own travel times, indeed. So that's one thing definitely to be careful of in combining decentralized usage with a system optimizing mentality, which is that you can only improve things by adding resources. Well, that's not true if you also have decentralized users. Maybe I can come back to refer to that sort of idea and how I don't think that's occurring in this situation later. So,
are you thinking of a decentralized situation or some kind of centralized organization?
Well, okay, so maybe we can achieve both. Mm-hmm. So the idea would be that a centralized view for how to assign traffic across the subflows could be achieved via decentralized actions, which are themselves coordinated via a pricing or feedback mechanism. So today, something of that nature is done in the internet, where single path traffic is coordinated via feedback. Whether you have lost packets reduces your rate, and if you're not having lost packets, you're continually increasing the rate. And the equilibrium under those conditions is a decentralized algorithm which achieves a system goal. And the similar story, similar mathematics, is underpinning what we're talking about here. The thrust of this talk is exploring the degree of robustness one gets with the n parameter. So I haven't got a lot of slides prepared to address that. Okay, well, we will need some notation, and I've tried to compress it onto one slide. It's reasonably straightforward notation. So the idea will be in our model of a network that we have, say, capital N nodes, and the edges J are directed edges, and also they have a capacity associated with them for flow, which is Cj. The most general situation would be that new connections arrive according to a stationary stochastic process for each source-destination pair labelled by S, and at the moment we can just focus on the rate at which connections arrive for a given source-destination pair, which I'll call nu sub S. Later in some simulations, I'll make that a little bit more concrete and think about a Poisson process whose arrival rate is nu S. And each of these stochastic processes for the different source-destination pairs will assume to be stochastically independent. A connection arriving at the network has associated with it a certain file size, a certain amount of data that needs to be transferred in that connection, and that file size will be taken from a random distribution. It's a random variable, and let's suppose that random variable has a mean, which is labelled ms. Later, we may look at some simulations where that distribution could be, for example, exponential, or often in internet studies, people like to look at Pareto-type distributions. So in our case, we'll look at Pareto-type distributions. The mean parameter ms plays an important role combined with the arrival rate in that their product, which I call rho here, is the rate of work arriving for source-destination pair S. So nu is the rate of connections. Each connection brings an amount of work on average ms. Sorry, I've mixed Greek and non-Greek letters here. Later, m, for symmetry reasons, will be set to 1, and so m will sort of disappear fairly quickly from most of the things. We'll just be left with Greek letters. Apologies for that. So what about the flows? Well, flows are between a source-destination pair, S, and flows may use a number of different routes labelled by R. So a route is then a path, a collection of edges joining the source and the destination end to end along the directed edge. And so if I let XR be the non-negative flow on route R, and these two matrices A and H will encode the network topology information. So the A matrix is the edge route instance matrix. It's 1 if edge J is on route R and 0 otherwise. And the matrix HS is, well, the rows label source destination pairs and the columns label the routes involved. So if route R connects source destination pair S, then there's a 1, otherwise it's a 0.
What is R? Is it a pair, a source?
R is a route along which our traffic flows, and there's a kind of excess of terminology here. You might want to call that a path in the graph. It's a collection of edges that join end to end with respecting the directed edge.
And is capital R the set of all possible paths in the graph, or do you have some pre-selected set of routes you're going to use?
So R could be as large as the full set of possible routes that connect a given source destination pair, or more typically it can be some constrained subset, maybe subsets of a certain minimal length, or minimal length plus 1. So preferred paths. Sorry?
Or maximal length, perhaps.
Or maximal length, yes indeed, yeah. Okay, there's little assumptions of that form at this stage.
So R in S means that R is one of the pair?
R is a route that connects source destination pair S. So it's a slightly non-standard notation, but it's helpful to do it that way. And the next bullet point is just saying that if I drop the suffix, then I'm talking about the vector of these quantities. So the vector rho has components rho S for each source destination pair. Similarly for capacities on edges, mean flow sizes, which I say are going to drop out soon, and flows themselves. Later, when we talk about the application in the multipath internet case, it's important also to have each route, that's to say a path of edges, has associated with it a round trip time, T sub r, which will occur in our formulas later. And it's also convenient to have the notation, well, gross notation here, that of SR, which is the source destination pair, which is associated with route R. So it's the terminal nodes of route R, labelled by the quantity S. So it's a lookup table for that. Okay, so given that notation, I think it's natural now to see that there is an interesting set here, omega, which is a collection of workload vectors rho S over the different source destination pairs that fulfill the following conditions. So these conditions are that there is some non-negative flow vector, flows across routes, XR, such that, so the matrix multiplication here tells us the total amount of flow assigned to edge J for each component here. That's exactly what this matrix will do for us. So this collection of flows is non-negative. It doesn't break any of the capacity constraints. And also, such a flow is compatible with a workload of rho, since that's what this matrix is telling us. So this collection of workload vectors is in some sense feasible. Okay? Such a vector in that set, the capacity region, that set, has associated with it an XR function, one per route, that fulfills our constraints. So it doesn't exceed any capacity constraints, and also it does deliver workloads of size rho.
So here, rho is the average, the mean workload. So this means that on the average, you are able to satisfy things, and then you hope that you can do it also with actual random.
Well, that's going to come later, but if we didn't sit in this set, we couldn't possibly expect the random case to work. So just at the mean level of...
yes.
Yeah.
I understand.
Okay. The reason for identifying that set is it's particularly neat to work with, so mathematically. So if I was to sketch out that, so let's take the case of just exactly two source destination pairs, so we can draw the picture. Then that set omega will typically be of this form. It's got linear constraints. It forms a sort of S-dimensional polytope of this form. And the capacity region is that workload vectors inside this set here, which on your screen is not as coloured as it is on my screen, for some reason. Such a workload vector in this region could be obtainable, perhaps. Certainly outside that region, we would say it would be infeasible because whatever distribution you used couldn't possibly meet the mean constraints. And it's very nice to work with this region because we can identify points on the boundary of that region by means of solving precisely a linear program, so a very tractable mathematical optimization problem, which is outlined here. So the way to see how this relates to the boundary point would be to suppose that you take a fixed ray through the origin. So that's to say we would choose, for example, let's say rho over bar. If I set those equal to ms, these are the means for the different source destination pairs, then that fixes a direction in our space over the source destination pairs. And if I multiply by a constant that vector, then I move along the ray. So what this optimization problem is doing is it's choosing the scalar alpha to be as large as possible so that we remain in that region. And these are the constraints for that region. So that linear program there for fixed vector rho over bar tells us the quantity alpha tells us this point here, how far we have to scale the rho bar vector to fall just on the boundary.
So ms is like the size of a message, for example?
What the average size of the message.
No, yeah, m is the average.
Yeah.
And do these definitions tell us or not, I didn't understand, whether you can split a message and send it in two routes or not?
This is the total amount of file to be downloaded when a connection arrives, which is at source and destination. So there's a quantity of information to be transferred between the source and destination, and it's going to do that over one or more routes between the source and destination.
So I can split a message.
Indeed, yeah.
Send it in two ways.
Yeah. Perhaps that refers to a very nice point. If I go back to the notation, which I didn't mention specifically, notice that the number of routes available to a given source destination pair is hard-coded into the matrix H. So that parameter n I was talking about earlier, the number of subflows, the number of routes available to a given source destination pair, would tell us the number of ones in each row of that matrix. If I adjust n, make it larger, then I'd have more ones. So in fact, this capacity region is for a given value of n. It's for a given route set available. It could be all the longest routes, or it could be the shortest routes, or something in between. So later, when we vary n, we'll also be varying this matrix H. Okay. Okay, and then just to complete this story, if you do use this linear programming problem, and with this identification that you fix your vector, your ray direction, to be the mean sizes here, then that product gives us alpha, the interpretation, as being the arrival rate, which is uniform across all source destination pairs. And what we're doing in this linear programming problem is fixing the m's, but scaling up a uniform arrival rate in such a way that we first hit the boundary. And that will give us the largest possible uniform arrival rate across all source destination pairs, which is still at least feasible. Are there any other questions about the basic model? Okay, so let's look at some toy network examples to build up some intuition. So this will be a toy network example for lots of reasons. First of all, I'll have a modest number of nodes, 10 nodes. I'll set all the file sizes to be 1. Also, I'll set the parameter n, the number of subflows available to a source destination pair, also to be 1. So this is more like the conventional single path TCP might be familiar with. And just to be clear, we'll always use the shortest path between our source and destination, which in this network is unique, I think. So in this situation, I've got 30 directed edges. So each one of these is actually 2 edges, 1 in each direction. And for each directed edge, I'll let the capacity be 1 unit. Okay, so where are the sources and destinations? Well, the sources and destinations are just the outer nodes. And these interior nodes are just sort of transit nodes. They're not themselves sources or destinations. So if we try to see how the calculations will go in this situation. So remember, n is 1, and each of the peripheral nodes has an edge of capacity 1 connecting it to the core network. This is a so-called single parented network. Each of the sources is connected to a single parent in the core network. Well, what's going to happen is that our upper bound for the arrival rate is going to come out to be 1/4. I could show you that by solving the linear programming problem. Alternatively, just imagine the edge from this node to the core. Well, it's carrying 4 single path flows, 1 to each of the other 4 nodes, N5, N2, N3, N4, and N5. And so the symmetry of the situation will lead us to an arrival rate of 1/4 and no more if we're to stay inside the feasible region. So that's very easy to obtain just by inspection in this network. We could also solve it in general by using the linear program in other cases. So that gives us a bound. What might we compare with that bound? Could we achieve that bound, for example, as suggested before? So I'm going to investigate that in 2 ways. One is via a crude queuing theoretic approximation to what's going on in into the multipath TCP, and a less crude so-called fluid model. So I'll start with the queuing theoretic one first, and that's to say, well, the use of a resource, a link in the network, I could perhaps, maybe it would be insightful to compare that with an MG1 processor sharing model. So if I just recap what that means, the MG1 just means that the arrival process has memoryless properties, so it's a +1 arrival process. So in my simulations later, we will definitely have +1 arrival streams for that reason. The G just means it's a general distribution for the service times, which is compatible with my earlier remarks about the file sizes. And 1 means that there's a single resource, a single server. The processor sharing refers to the idea that that single resource is being shared out equally between all of the jobs currently in the queue. Now, for such a MG1 processor scheduling model, it's known that the mean number of jobs, the mean number of connections, is insensitive to that file size distribution, for that service distribution. That goes back to work at Kleinrock. And so it's quite straightforward to write down what the mean number of connections would be on a MG1 processor sharing model for that single link connecting the outer node to the core. And
can you say again what the sharing means?
The processor sharing.
Yeah, I know what an MG1 queue is, but I don't know what the sharing
Okay, so processor sharing is a variant of the usual first come first serve MG1 queue, where instead of customers being served in order of arrival, what happens is that the server partitions itself across all the current jobs, not just the earliest job arrival, but all the jobs are served together, and they're served in equal amounts.
But in a slower amount, depending
Correct,
on how
yeah,
many
so
there
it
are.
partitions itself into sub-servers, if you like, 1 per current job.
So actually there's no queue.
Correct.
It's a queue without a queue.
Indeed, yeah. Okay, and that has very nice properties about insensitivity to the file size distribution. And indeed, the formula for the mean number of jobs in a MG1 process sharing queue would be the traffic intensity divided by 1 minus the traffic intensity. Well, the traffic intensity on an edge in this network is 4 times the arrival rate, so there are 4 streams going through that edge. So if the arrival rate is new, then the mean number of connections ongoing in that edge would be 4 new divided by 1 minus 4 new. And so the mean number of connections throughout the whole network would be 5 times that, since there are 5 outer nodes, 5 sources. Okay, so that formula there is an interesting and useful one to compare with our bounds, and also we'll have a fluid model as well.
Does this also say that the average time until you complete your connection is roughly 1 over 1 minus 4 US in your case here?
Well, this is the mean number of connections,
Yes,
but you
yes,
could,
I know.
using Little's law, you could get to the mean time.
Yes.
You could. Okay, so this would be the basis of a MG1 processor sharing model to try to capture what was happening in that toy network with 5 nodes. I'll also want to compare that with another model, so-called fluid model. So this is a little bit more detailed, and what we'll do is let me just skip this slide and I'll come straight back to it when I need it. So just to compare the MG1 processor sharing model, so that gave us a function of rho, which if we plot the mean number of active flows, that function is the blue dashed line, and obvious from the formula, that has an asymptote just at a quarter. So the interpretation is that from the linear programming, the capacity region idea, you've got an upper bound on the arrival rate, which is going to be a quarter. If you had a MG1 processor sharing model for how flows were being dispatched in the network, then you would be left with this dashed line here. And what I'll do is go back to the previous slide where I'll talk about a fluid model, which gives us a means of obtaining these other simulation results, which are somewhat like the MG1 processor sharing. Okay, so if I go back to the fluid model, so the fluid model is now taking us much closer to the internet-style congestion control, which is a feedback-style control. Let me just state it as a mathematical object, and then I'll give some of the intuition for where these different components come from. So the mathematical object that we're going to study is a collection of coupled ordinary differential equations, and these ordinary differential equations are going to be first order in the flows x. So there's one of these equations for each possible route r in our set of available routes. And how are these coupled? Well, they're coupled because, for example, xr, the first derivative of xr, depends on ys, but ys is the total flow over all routes with the same source destination pair s. So different x's will affect y, which will then affect x. So these are coupled ordinary differential equations. And how are these ordinary differential equations used? Well, the idea is that we would have what we call a bi-level simulation. The idea would be that you would have an arrival process of connections, which would be a Poisson process, one such arrival process per source destination pair. There'll be independent arrival processes. A connection accepted into the network then drains the file through the available routes using a sending rate XR. So what are the XRs? Well, these are going to be the outputs from solving this ordinary differential equation. So if we were to solve, for the equilibrium behavior of this ordinary differential equation, so the crucial piece of terminology is here maybe. What we're going to say is that at time t, we're going to initialize these ODEs in the dummy variable u to be the current values x. Then what I've done in the numerical simulations is to pursue these ODEs, and to the extent that they have stationary equilibrium behavior, I'm then going to use the outcomes, the steady state x's from these equations, as the new source rates from time t onwards. And so we'll run with a piecewise constant source rates x determined by the equilibrium outcome of those ODEs until something needs to change. Something may need to change because either a new connection arrives, so a new point in the Poisson process, so the number of connections in the system changes, we'd need a new solution to the ODEs, or alternatively, one of the existing connections drains its file download completely till there's no more traffic to be sent, and so it too is a connection which sort of drops out from the active set. So again, we'd need to resolve for the equilibrium behavior. We could also do indeed various related studies have looked at perhaps a more sophisticated variant where instead of having piecewise constant rates x until we need to change because of a new connection or a file download completing, what you could do is run with the time-dependent solutions to this. So you'd start at time t with your current flow, and then you'd run with the source rates that would be driven by this system of ODEs over time. So we haven't done that, although one could do that. And that would give you a time-delayed system of ODEs at the same time. Okay, so let me try and explain some of the intuition behind this system of ODEs. Okay, so first of all, so we're looking here at the rate of change of the source rate x. So this is important to know whether it's positive or negative, whether we're increasing the x or decreasing the x. So the sign of that is governed by the right-hand side here. So let's think about this expression in the square brackets. So first of all, there's a little bit of notation which I haven't defined on the slide, but let me explain it here. So this square brackets with the plus just means that when x is positive, this argument here is positive, then we'll use the expression in the brackets. But if x is 0, where x is non-negative, if x is 0, then we'll just use the positive part of that expression. So that's important because you want dx by dt to increase or decrease the x, but in the non-negative range. So if x goes to 0, you don't want to let dx by dt be negative, because then x will go negative. So it's just a way of dealing with this boundary condition if x is 0. But to the extent we keep x in the positive orthant rather than on the axis, then this will just be transparent, and we just have this expression here. So this expression is the difference of these two terms. So if we start perhaps with mu, so mu is some function p of the total flow on edge j, which is what this sum is doing here, the total current flow on xj. And so we might think of p as being a penalty function, or maybe in the feedback context, we think of it as a marking rate or a dropping rate of packets being sent on this connection. It's one that will, with this particular functional form, it's one that will increase rapidly as the argument z approaches capital C, the capacity on the edge. So it will give a penalty to coming close to, or indeed exceeding, the flow values equal to the capacity. So this is a marking or loss rate when the traffic on the edge j is given by the current values x. Then this term 1 minus lambda is just the product of 1 minus mu. So that's the probability that our flow is not being marked or dropped. Whereas over here we've got lambda, which is 1 minus that, which is the probability that we are being lost or dropped. And so these two terms, the difference of these two terms will indicate whether we have a positive or negative derivative, so whether x is increasing or decreasing, and the equilibrium behaviour of this will be where these two parts just balance. This is an example of so-called additive increase, multiplicative decrease. Multiplicative because there's a y here and there is no such y here.
Where does the 8 come from? Is it just a decision that you made, or does it follow from something?
Okay, so this functional form here, let's say I had a factor beta rather than beta equals 8. So this form here with beta, then beta would be a control parameter which says how the link, how sensitive it is to traffic near the capacity. So if the larger beta is, the more sensitive it is. Another way to think of it is how steep is the penalty function in a sort of constrained optimization underpinnings for this. Y8, which is your question, so 8 is one that's popular in the literature, so it's a useful thing to choose. Also, these ODEs, this coupled ODE formulation for the multipath problem, which is formulated and constructed in the paper by Kelly and Voice, What they go on to do and include in their paper is to note a network stability condition for the various parameters, the A's and the B's, and how sharp the penalty function is. So the A, the B, and now the beta. They have a condition which says if A, B, and beta all satisfy that condition, then it will be networked, be stable. And this choice 8, beta equals 8, is helpful in making those. So that's quite a long wordy description in a rather mathematical sense for a protocol, an important protocol that is now being studied in many guises from field trials and so forth for a multipath TCP model. And if we follow that idea of plus on arrival streams and then ODEs solved to their equilibrium to give us the piecewise constant rates, then that leads to outcomes such as these. So if I fix the arrival rate and then were to simulate such a network as the toy network with 5 nodes, 5 source nodes, for different arrival rates, and then examined the mean number of connections in the long run present, mean number of active presents, and that grows with the arrival rate and follows results like this with standard errors of this form. So the MG1 processor sharing is not completely capturing what the fluid model is capturing, but it's, well, it certainly seems to have the same sort of idea about the asymptote, the capacity bound, and it gives some insight into the behaviour of the fluid model. Okay, so that example gathers up lots of preamble about the different approaches, the fluid model, the MG1 processor sharing type model, and integrates it with the linear programming to give the red capacity constraint. So let's look at that in another situation. I can be a bit more rapid now. So in this situation, a so-called dual-parented network, dual-parented because each of the source nodes has 2 parents in the core network. So we might expect this to be more resilient to mismatches of traffic or capacity failures, because if I allow n to be bigger than 1, say n equals 4 in this example, then each connection between, say, n1 and n4 splits itself over 4 shortest paths between n1 and n4, which are usually 4 distinct paths unless your 2 nodes are in fact neighbours. Okay, so in this example, n has been increased, but also the network topology is now different. It's got the dual-parented form. And if we think about the MG1 processor sharing model, so this is the term coming from the sort of traffic intensity divided by 1 minus the traffic intensity. So why is the traffic intensity 2 nu? Well, if the arrival rate of connections is nu, then the 4 subflows would be split 2 on each of these links into the core network. And the arrival rate of subflows would be 2 nu on each of these edges, since there are 2 subflows, 2 of the 4 subflows. There are 10 source destination pairs, so that would 10 times this would give me the total mean number of connections, total mean number of subflows, and so the total mean number of connections is 1/4 of that, because each connection has 4 subflows. So this argument gives us this formula here for a MG1 processor sharing approximation to the number of mean number of active connections. The linear programming gives us a value of 1/2. And the way to see that would be to just note that we've got these 2 subflows on this edge. Capacity is 1, so have an arrival rate greater than 1/2 there, or arrival rate of connections. And so if we look at the results in this case, so here we've got the upper bound of 1/2. Now the queuing approximation doesn't look quite as insightful as it was earlier, but we have now the fluid network model of this form. Okay. So in the remaining 10 minutes or 5 minutes or so, I'd like to look at some further examples, and these examples are to illustrate well, the degree to which multipath is useful, And it's useful in two ways. I think either that it improves the performance, the total arrival rate that you can sustain in your network, or it's useful because under some failure conditions or mismatch conditions, the use of multiple paths allows you to adapt your traffic pattern to what's available. So the first of those perhaps we can look at here. So if I take another network, so now I've got this is a 3 regular network, so every node has exactly in degree 3. There are 18 edges with all sorts of non-uniform capacities as shown by the numbers here. So these are the CJs, the different arcs. And if we suspend the discussion about the fluid model and the MG1 model and just look at the capacity bound. So we obtain that by solving a linear programming problem. It's not a huge linear programming problem in this case. It's very easy to solve such linear programming problems. And we obtain the following for the capacity bounds. So this is the horizontal intercept for the red dashed line in the earlier graphs. So if n is 1, if we were only using single path TCP, just thought about a single route for each source destination pair, then for that rather irregular 6-node network we just saw, we would have a mean number for the arrival rate being 0.66. But if we augmented it so that we had 2 subflows rather than 1, then the capacity bound shifts to quantity 2.
Is this general or related to the previous picture?
No, it's just for that network. Yeah, for that precise network, you have a linear programming problem to solve, it's readily solved, and the outcome wouldn't be something we could do by inspection as we did in the early cases, but it sure isn't difficult to obtain numerically that value.
So the number of flows is determined by the graph. What do you mean by if it's 3, if it's this?
If the parameter n equals 1, then I didn't tell you what the routes were, but there was exactly 1 per source destination pair, and it would be taking the shortest path. If there was,
it's always shortest.
yeah, there's no ambiguity about that in this network. In the case n equals, we allow n to be bigger than 1, so n equals 2, for example, then instead of taking just the unique shortest path that existed in the network, then I would give it 2 paths, and they would be minimal in length, I think. Yeah. Be more precise about exactly which paths there were, but there were 2 of them, and they were sensibly chosen. So the arrival rate that consistent with the capacity region has gone from 2/3 to 2, so it's a tripling of arrival rate if you allow yourselves 2 paths rather than a single path. So in some sense that's giving us some virtue for using multipath rather than single path. And if you increase to n equals 3, it goes up again by 1.5 to 3 1/3. But after that, if I increase n by more than 3, actually there's no increase in the bound. So it's essentially saturating. Looking back at the previous network, it's saying that I could offer more routes, more than 3 routes per source destination pair, but there wouldn't be any benefit, at least in terms of this capacity region. It wouldn't enlarge the capacity region.
It's probably simply because there were only 3 outgoing edges.
Yes, but not precisely that, but that's a typical number. We'll see later some other examples. So, okay. So that, in a way, gives us a descriptor which allows us to, in this sense, quantify the benefits of multipath, and also to note that they may saturate. So I needn't have a gratuitously large value of n, which might overwhelm the coordination problems in the protocols. A modest value of n gives us a large amount of the resource pooling that's available in this network. That's what these results are saying. Okay, and just to come back to that point. So suppose we took a much larger network of 50 nodes, n equals 50, and I haven't tried to draw this picture, but it was chosen so that it was, again, a regular network, and here had degree 15. The early one had degree 3. Then the story is, it seems, for that particular network, that the capacity region does enlarge quite nicely as you go from 1 to 2 and from 2 to 3, the number of subflows per source destination pair. But then we see this saturation effect. It, I think, saturates at n equals 6.
So you see that it's not a function, doesn't depend
It's
on
not
the
equal
host
to the degree in a
You
regular
would have
network.
predicted that it would stop at 15 or something,
Yeah.
right? You can actually,
Yeah. So I think the degree is helpful. Higher degree networks will give us more scope for multipath benefits.
up
But
to
it
a
isn't
point
what
which is much lower than the degree in this example.
Exactly, yes, that's right. So we haven't looked at it here, but I think this would be a nice, future work would be a sort of network science type in study where for a whole range of networks with different degree properties and so on, you calculated this linear programming problem which gave you the capacity bound. That's an easy computation to do. So I think you could start to chart out what would be the correspondence between these bounds and say the degree of certain families of random networks. I haven't done that here. Okay, so I think through the linear programming, through the capacity constraints that we get from the capacity region, we can sort of start to appreciate the sort of some insights about the benefits of multipath, but also that it will saturate, just go on, keep and get benefits. So just to finish briefly, then I'll look at some of these resilience or robustness questions. Again, I've got a couple of fairly toy examples to illustrate. So this is a very nice toy example. It has nice symmetry properties in the network, which make it particularly straightforward to work with. So in this example here, I've got sources and destinations. So I've got the colours that don't come out too well, but these sort of slightly pinky ones at the top, N1 and N4, are a source destination pair. Similarly, N2 and N5, and N3 and N6. On my screen, they're lovely different colours. On your screen, they're minor perturbations, all of the same colour. Okay, and then each of the directed edges has capacity C, which let's suppose all of them are capacity C equals 1, except I'm going to investigate what happens if I make this a parameterised capacity C, and I'm going to drop C from the maximum value 1 down to 0 by adjusting this quantity F. Now, a very nice thing about this network is suppose that you had n equals 2, so 2 subflows. So notice that each of these pairs, source destination pairs, has exactly 2 3-edge paths between them. And if I was to, say, remove that edge, then the
that was one edge you didn't need to
remove the projector. Okay, so something.
Yeah. Yeah, that's the thing probably.
Okay, right. As I was saying, so if I remove this edge, these 2 source destination pairs, the top and the bottom, should we call them, both of them have a path that uses this edge, and let's say they both will therefore have to use just their single path at the top and the bottom, which puts more stress on these edges. But this edge here is also being used, say, by N2, N5, sorry, N3, N6 here. So the edge lost here causes traffic to shift over to the top and the bottom, and the whole thing is completely symmetric. Every source destination pair has 2 available paths, and every middle edge has 2 source destination pairs that use it. So actually, again, by inspection or alternatively by solving this linear programming problem, if I set n equals 1, so there's no potential to overflow at all, then the total, the uniform arrival rate that this network would support, if the capacity is 1 minus f on this edge, would just be governed by this edge here, and so the arrival rate can't exceed 1 minus f, because the single path traffic through that edge has nowhere else to move to. But if n equals 2, then each of these paths can overflow to their alternative, which avoids that edge, and so the constraint would be the total capacity given by these 3 edges. Every source destination pair must use at least one of these 3 edges, And the total capacity here, well, it's 2, the top and the bottom, plus the broken one, 1 minus f, and there's a third of that. So the third of that total capacity is shared across a single source destination pair. So just to illustrate in a picture, what that's saying is as I adjust that factor f, if you're single path, then you go down like 1 minus f, and you don't go down anywhere near as steeply. Okay, it's a trivial model, don't go anywhere as steeply in the multipath case when n equals 2. That's just to build up some intuition. Let's suppose that instead we did so in that sense, multipath is more resilient and robust to the edge capacity being eroded on the central edge, since the arrival rates can be much higher. I'll just finish with this example here, which is a nice example, which actually goes back to ideas of robustness in telecommunication networks. So the idea would be, rather than adjusting edge capacities for failure type of scenarios, maybe you have a mismatch of traffic and capacities, traffic and resources in the network. And this mismatch is going to be one that's going to be parameterized by the parameter delta. And so how do we form a perturbed traffic matrix? Well, we do it in the following way. Let's suppose we have a nominal uniform arrival rate mu sub 0, and S is the collection of source destination pairs. So what we're going to do is we're going to let sigma be the collection S, and while the size of sigma is still greater than 1, what we're going to do is choose 2 distinct source destination pairs from the collection of source destination pairs sigma. And for that pair of source destination pairs, we'll choose a random amount of traffic and swap between them. And the random amount of traffic is going to be given by the quantity u, which is uniform on the range 0 to, so mu 0 is this nominal initial traffic, let's say fraction delta of that. So the range is 0 to delta times mu 0, and that amount u, sampled from that distribution, we subtract from the source destination pair S1, and you add it to the source destination pair S2. So that has the very nice feature that the total traffic offered is constant at all times, and you simply, according to how large delta is, you randomly perturb it by more and more the larger delta is. And you keep doing that for source destination pairs until you've examined all of them. You can't shift it between pairs, any further pairs. So that gives us a non-uniform traffic matrix, and it's the degree to which it's non-uniform is parameterized by the quantity delta. If you then solve these linear programming problems to work out the arrival rates, then in fact the multipath for our network with n equals 2 is completely insensitive to this choice of delta, because each of the source destination pairs has one alternative it can shift to, and they do so equally. Whereas the single path TCP is eroded as delta gets larger and larger, up towards 1, towards 100%, then the arrival rate is decreased. These are simulated, these are random traffic patterns, so I've simulated over many runs of this random realization, so these are in fact interquartile ranges for the arrival rate at that point. Okay, so multipath is much more robust both to link capacity failures but also traffic mismatches. So I'll finish here, so just summarise what we've looked at in the talk. So it's possible to construct upper bounds on the arrival rates with multipath protocols, and that upper bound is one that appears to be quite approachable by a variety of models that seem appropriate for multipath TCP protocols. And such a bound can be constructed by means of a linear programming problem, which means that we can get some insight into the behaviour in large non-uniform networks through solving linear programming problems, even where the simulation type approach would probably be undermined by the size of the problem, in a way that linear programming simply isn't. And at the end, multipath leads to load balancing and resource pooling, which is more effectively utilising the resources, but also leads to rather more resilient network behaviour. Okay, I'll stop there, and there's a reference which people are welcome to study.
First of
Some people have to leave, so yeah.
I wasn't totally clear. You're not talking about the route selection scheme, but there's a link destroy path in the multipath cases?
Not necessarily.
Because it seemed like some examples they weren't and some they were. So,
yeah.
So you're, I mean, in each
so the
case,
formalisation doesn't require them to be link disjoint, and in some circumstances they would have been by design, in others maybe not, but you could impose that.
Yeah. But you're assuming somebody gives you a multipath route calculation scheme, and it's not just sort of k-shortest path, it's just some scheme, and then you're doing the rate assignment.
In fact, even better, they should give me the H matrix, which encodes all of that information there and then.
It's worth pointing out, people may not realise that if you have an iPhone and use Siri, Apple actually use this so that you download the audio coming from your Wi-Fi and your cellular data, and they do the rate assignment using some scheme we don't know what secretly, but it's actually this stuff is, and they adopted it really fast when this theory all started coming out. They did it. So.
I think load balancing, resource pooling is a really important topic to embrace with flows in networks, communication networks certainly, but also road transport networks, energy networks, all sorts of networks can benefit greatly from resource pooling.
This is all based on the average, on the MS or M's, which are average, right? You don't, the distribution of these loads does not play a role. Right?
Right, so formally it doesn't play a role in the MG1 processor sharing because of the insensitivity result. It's only sensitive to the mean of the distribution, not the actual distribution. That goes back to Kleinrock for, that's a very nice property of MG1. But the fluid simulations certainly do depend on the distribution through more than just the mean. So I think on the slide, so the simulations given by this black results here were for Pareto file sizes. So there was a simulation, so it was Poisson process of arrivals. Each arrival comes with a Poisson, each arrival comes with a Pareto file size. If you choose the parameters as shown here, then it does have a mean, and the mean is 1 by that choice of parameters.
If you have very large systems, does it get less and less dependent on the distribution?
In large systems, large in the sense of numbers of nodes and edges. I could do, I mean,
some kind of averaging because the system is large?
Yes. I can't think of a formal answer to that, but plausibly that might be the case, yeah.
Well, wouldn't that have something to do, that seems to have something to do with n as well, right? I mean, what you choose to be n to be. Because obviously, even if you have a very large network,
yes, so the larger n is
equal to 1, you still have.
Yeah, so n, if you like, is this, encourages mixing of flows over the network.
Yes.
The larger n is, the more mixing, and maybe therefore some regularity will occur in the stochastics. That's right. But, I don't have any formal results on that. As I say, I think this is a ripe area for investigating for sort of latest network science perspective of families of random networks, but also, as you suggest,